Swayam Prabha. Digital India. Educated India.
Hello all, welcome again to Astrochemistry. This is lecture number 62 and tutorial 16. So in the last class, we were discussing about the different types of rigid rotors. That is the last tutorial. And we were discussing about the different types of symmetric tops. One possibility, which corresponds to methyl chloride right here, trichloromethane, sorry, is the idea that the two different moments of inertia are distributed such that the greater value, the degeneracy is seen in the greater value and the uniqueness is in the lesser value of moment of inertia. The other possibility is, I wrote it down in the earlier class but deleted it, I'll write it down again here. That is IA equals IB, which is less than IC. An example for this is what we just saw, methyl chloride, and an example for this type is what is called as benzene. So these are the two different types of symmetric tops, and regardless of what type of symmetric top that we are talking about, this idea is going to be holding good. That is, there are going to be two different types of quantum numbers and two different rotational constants. Okay, please understand that. And of course, this is within the rigid rotor model. If we are going to be including distortions also, there are going to be more terms added to this. All right, let's not worry about that for now. Are we clear as to what we are dealing with? Now, what is the astrochemical implication of this particular aspect? Okay, I'll express that here. The astrochemical implication astrochemical implication due to the idea of the reduction in the number of moments of inertia along the principal axis is that for a molecule like benzene, right, there are some patterns in the microwave spectrum. Okay, right? So there are some patterns in the microwave spectrum through which you can actually easily, you can easily identify the fact is there are going to be two rotational constants, and corresponding to this corresponding to the K quantum number, you'll be having some branch, and similarly corresponding to the J quantum number also, you'll be having some branch, right? And due to this symmetry, you can identify them easily. Okay, right? Identify such molecules in space easily. So when I say easily, I mean I'm talking about relative to some other more difficult molecules wherein there is no symmetry present. Okay, right? So this idea that it's not completely asymmetric, it's not a completely lost case wherein like you have three different values of moments of inertia, but that you can systematically club two of them via some equality relationship, right? And then there is going to be another value that leads to some pattern in the microwave spectrum, and using this pattern, whatever you get in the lab could be compared with what is obtained from the interstellar medium, and you can detect these molecules much more easily. Okay, right? So this is the idea of symmetric tops. The next class of molecules, I'll delete this part now, and the last class of molecules are what are called as, I think this is D, sorry. the last class of molecules is what is called as asymmetric molecules. Or tops. Okay, now an example of this would be water or CH2Cl2, etc., etc. Okay, right? So now you may think, hey, water is a simple looking molecule, right? But even for water, where will the center of mass for water be? Just based on intuition, what do you think? Is it first of all going to lie on the assuming these are point masses, is it going to be lying along this HOH line? Is it going to be closer to oxygen or hydrogen? It turns out that it is going to be lying somewhere here. Okay, right? I mean, this is not a lone pair. So these are the lone pairs. I'll write the lone pairs here. And this is where the center of mass, denoted by this point C, somewhere closer to the oxygen. Okay, right? So now with water, okay, right? You can easily therefore see that when you use the formula I equals sigma or I mi Ri square, right? The Ri's are not going to be the same along any three directions. So therefore, for a molecule such as water, your IA is not equal to IB is not equal to IC, which implies that the microwave spectrum is going to be rather complicated. Okay, right? Microwave spectrum rather complicated. And what is the astrochemical implication? It is also why, especially a molecule such as water, one reason, not the only reason, one reason why water was not the first molecule detected in space. Recall, approximately some 20 or 30 lectures earlier, right? We were discussing that the first molecules to be detected in space were what? There were CN, CH, and CH plus. And even after that, it was ammonia, which was detected in 1960s. Water was detected only around 1976 or 77, if my memory serves me right. Okay, right? So the fact that the microwave spectrum of water is complicated enough is one reason. It's not the only reason. There is one more reason which we shall very soon see in the next module. Okay, right? When we discuss astronomical spectroscopy. Okay, but one reason why water was not detected earlier. Okay, why water was not detected in ISM earlier. All right. So because the microwave spectrum is complicated, it was difficult to assign the values precisely and then observe the same pattern from in a light sample obtained from space. Okay, right? So that is one reason why even for a simple molecule like water, right, the microwave spectrum is going to be looking fairly complicated. Okay, there of course are many more molecules. Now this also explains to you why a molecule such as for example, take the simplest of amino acids, glycine, etc. They have not been detected in space. Okay, right? They perhaps may be there, but the definitive assignment of peaks is going to be tremendously challenging. If it is going to be challenging for water, recall how challenging it should be for a molecule containing many more atoms. Correct? Okay. So these are the different types of rigid rotars which are used in microwave spectroscopy. And all of these, okay, right? Each of these different types has a story to tell with regards to the astrochemical implication, right? So that's why microwave spectroscopy is absolutely critical to detect molecules in space, as I have been repeatedly telling you. Okay, it is useful. It is critical in the sense that it explains why some molecules can be detected via microwave spectroscopy, which is a majority of the molecules so far, and why some molecules can also not be detected. Okay, in fact, it's only now I'm slightly jumping ahead of myself. Okay, right, in the sense that I should be telling this in the next module in a more focused way, but in a scattered way. I'm just telling you matter of fact that it's only in the recent, let's say, approximately 10-15 years that we have moved slowly beyond. We are beginning to move slowly beyond just microwave spectroscopy to detect molecules in space. So this is due to the advancement in spectroscopic techniques, as well as the facilities, having like space stations above the atmosphere of Earth, etc., etc. Okay, so in short, microwave spectroscopy is important, and the various concepts associated with microwave spectroscopy are also of critical significance in astrochemistry. Okay, with that, we move on to our next question in this tutorial. So now the next question is going to be, what are the specific selection rules in rotational and vibrational spectroscopy? Now, I think the phrase selection rule itself might not be new to you, right? When did we discuss this? When I was talking to you about the transition moment integral, right? The transition moment integral, the mu fi, right? We had spent at least 1 or 1.5 classes explaining the significance of it, although we never computed it, okay, right? So I think this was around lecture 45 or 46, okay? You may please go back and look up the exact number. So in those lectures, I was telling you about the significance of selection rules. The computation of the transition moment integral leads to both specific and gross selection rules. The gross selection rules also we've seen even before the introduction of the transition moment dipole, the transition moment integral. We saw that for a molecule to be purely, for a molecule to exhibit pure rotation spectrum, it must have a permanent dipole moment. In other words, it should be a polar molecule, right? Within the rigid Rotor model, of course, okay, right? Then the next idea we saw was also that for a molecule to exhibit a vibrational spectrum, that is like it should be, for it to be IR active, its dipole moment should change in the course of the molecular vibration, right? These are gross selection rules which were obtained from calculating the transition moment integrals, right? But we never did the calculation itself. I'm just saying that, just by looking at that, because some terms should never vanish, these were gross selection rules. Now we are coming to the specific selection rules, okay, right? And how are these obtained? So the answer is, I'm just going to call them specific selection rule, SSR, okay, right? So the specific selection rules are obtained by computing the transition moment integral, which we are not going to do in this class. Because it involves calculating some integrals. It's not a difficult thing, but it is definitely time consuming. And because I have to teach you so many more aspects in astrochemistry, that could be reserved for a more specialized course in quantum chemistry or molecular spectroscopy. Okay, right? So you could obtain the specific selection rules by computing the mu fi. So what we're going to do is, we shall exclude the math or the computation and only talk about the final results. Final results, okay, right? So that's what we're going to do in this class. So we're talking about the selection rules, right? Recall that the selection rules are going to be expressed in terms of what? If you remember, I told you that the selection rules are going to be expressed in terms of, the specific selection rules are going to be expressed in terms of what? I had informed you about this around lecture 45 or 46. The answer is, the specific selection rules shall be expressed in terms of the quantum numbers. Okay, right? I also told you that 3 quantum numbers arise from the spatial part of the wave function and 1 from the spin part of the wave function. Okay, right? So in this particular case of rotational and vibrational spectroscopy, the the quantum numbers that we're going to be talking about are the rotational quantum numbers that we saw, right? J and K. J for any diatomic molecule, pure diatomic molecule or a linear molecule, and K for the symmetric tops, right? And the vibrational quantum numbers. So the vibrational quantum numbers that we saw was nu, right? So what are the bounds of J? J can be any integer starting from 0, and K is always less than J, right? Similarly, my nu is going to be starting from 0, and it can be an integer also, all right? So the specific selection rules can be expressed in terms of the rotational and vibrational quantum numbers, all right? So for vibrational spectroscopy, the selection rule is that for diatomic molecules, we need not consider, a single atom at all here, okay? Because the minute we talk about vibrational and rotational spectroscopy, we're talking about the spectroscopy of molecules, okay? Right? For diatomic molecules, delta nu is equal to +1 implies a transition is allowed, right? Else forbidden. And again, I'm not going to repeat myself again, but I've already told you in the previous lecture as to the meaning of allowed and forbidden. Forbidden is not like some eternal forbidden, okay, eternally forbidden thing, which can never occur. There are other mechanisms through which forbidden transition can also happen. Forbidden simply means that the intensity of the transition is going to be very mild, okay? But an allowed transition means that the intensity is going to be very high, okay? Please understand that. So this is for the vibration of diatomic molecules, and vibration of polyatomic molecules, right? It is hard to give the selection rule without knowing what is called as, the chemical application of group theory, okay? So I just call it beyond the scope of this course. Beyond scope of this course. I mean, if you ever, have a course with me on molecular spectroscopy, I'll of course talk about this in great detail, where you have to talk about what are called as the reduced representation for each mode, and then you have to see, which of them cancel out and which don't, and then you have to see when this integral has a finite value, etc., etc. For our purpose, let us say that we'll just limit the discussions to diatomic molecules only as far as the vibrational spectra are concerned. Okay, so this is for vibrational spectra. As far as rotational spectra is concerned, right? For rotational spectrum, the selection rules, the specific selection rules are that, these of course are the SSRs. The specific selection rules are that, again, A, for diatomic or linear molecules, delta J is equal to ±1. And note that here, of course, we are talking within the harmonic approximation model, okay, right? Within harmonic approximation. So here we are talking within the rigid rota approximation. Within the rigid rota RR model. Okay, so delta J is ±1. And for symmetric tops, recall that there are going to be two quantum numbers, right, besides J. For symmetric tops, there are going to be two conditions. One is that delta J should only be 0 or ±1, and delta K should be 0 when K is not equal to 0 and delta J equals plus minus 1 and delta K is equal to 0 when K is equal to 0. Okay, so please note these selection rules, right? And when these selection rules are going to be holding good, the transition is allowed and fast. Okay. Otherwise, it's forbidden and slow, and I would say, not intense. So it is going to be fast and intense. Okay. So what is the relevance of these specific selection rules in the context of astrochemistry, though? It is that, so in astrochemistry, why do the specific selection rules matter? It is because we detect molecules by comparing the spectrum obtained, from, let's say, the ISM with what is known on Earth. Okay, right? Detect molecules by comparing spectra from ISM and then on Earth. Now, I think I may have already told you in a lecture that the spectral transitions in the ISM, right? They need not be allowed. Okay, right? They need not be allowed by the selection rules because of what? Because it doesn't matter if it is slow. The order of transition can happen over millions of years. Okay, right? Whereas on Earth, right? The order of, you don't have an infinite time. Okay, right? So the transition can happen only in a matter of picoseconds or something in the majority of cases. So therefore, right, the fact that some forbidden transitions are absolutely not at all forbidden in the ISM, right, can lead to some discrepancies in our understanding of certain signals. Okay, right? And that is why one should be aware of the selection rules when actually detecting a molecule in space. You understand what I'm saying? Okay, right? So we detect molecules by comparing spectra from the ISM and on Earth. So therefore, which implies need to be careful because many forbidden transitions readily occur in ISM. I'm absolutely positive that you may not understand what's written here. So what I've written here is that one needs to be aware of the selection rules, right? Because some transition might be very feeble or extremely less intense. In fact, the phrase less intense, okay, or not intense is an understatement. A better phrase is feeble. Okay, right? So a signal can be extremely feeble, right, when you get it on Earth, but then it could be highly intense when you get the same signal from the ISM, because the time scale doesn't matter as far as the interstellar medium is concerned. Okay, right? So please understand that this is an important fact. Okay, the specific selection rules are also important when we actually compare the spectra obtained from space versus what we obtain on Earth. Okay, and I'll again read what I've written here because it's written in the bottom part of the board and my handwriting is pathetic. Okay, so we need to be careful because many forbidden transitions readily occur in the ISM. And why is that? It is due to the large time scale that is available in ISM. I've already told you this, I think positively in lecture 45 or 46. Okay, so these are the selection rules as far as purely rotational, this is for purely rotational spectra. Okay, right? And they are important in spectroscopy, but in comparison, for comparing with the spectra obtained from space, one must be careful and take this also into account along with the line width. Okay, right? So that is the significance of the idea of specific selection rules in spectroscopy within the realm of astrochemistry. Okay, now what I'll do is, in the remaining time, I'll just solve one more problem, one quick problem, and in the next tutorial, which is going to be tutorial 17 and lecture 63, I will just give you a sneak peek of the specific selection rules involving transitions for electronic transitions involving atoms. The electronic transitions involving molecules, there are some rules for diatomics, and of course for polyatomics you again need a knowledge of group theory. Okay, it is more complicated, but I'll give you a sneak peek into what happens with the electronic excitation of atoms. Okay, that should be done. Only a sneak peek though. For more details, you should actually go to a course exclusively meant for astrochemistry. Sorry, spectroscopy. Okay, this is astrochemistry, but in a course exclusively meant for molecular spectroscopy, you'll be getting so many more details. All right, yeah. Okay, so what I'll do now is, in the remainder of the time, I will just, this is going to be the third problem in this tutorial series. It is that, show that my delta nu bar, right, is given by 5.3 by tau centimeter inverse per picosecond. Remember, we had used an expression. We had used this expression to get the natural line width. Okay, a homework for you would be to identify where this expression came. Okay, right, where it is even coming from. Okay, right. So what is the starting point? The starting point is going to be our Heisenberg's uncertainty principle, right? Delta E times, let's say, like my tau is the lifetime of the complex, okay, right, is equal to h bar. Now you may be wondering why I'm using here h bar and why I'm using the limiting case. Okay, right, we use the limiting case, that is, I'm using the equality sign and not the greater than or equal sign to get the minimum line width. Okay, right? So I'm going to start off with this. The other question you may have is, why am I using h bar and not h bar by 2? Well, traditionally, spectroscopists have been using this h bar and not h bar by 2, even though more strictly speaking from a quantum mechanical viewpoint, you should be using h bar by 2. Okay, so we're going to start off with this, and I'm going to write delta E as nothing but h times hc delta nu. Okay, right? E is equal to h nu. So this is going to be hc over delta nu bar, because this is hc by lambda. So this is therefore hc delta nu bar. Yeah, correct? Because it is in the wave number that we're going to be talking about the uncertainty. So that times tau is equal to h bar, which is h by 2 pi, right? So then I'm just going to cancel out these two aspects right here. And so I'll be getting my delta nu bar as 1 by 2 pi c times 1 by tau. And if you actually work out the units, this number is going to be 5.3. I'll give that to you as a homework. Okay. So on that note, I end this tutorial. And to sum up, what did we see in this tutorial? We continued our discussion on the different types of rigid rotars, and I was talking to you about the specific selection rules in spectroscopy and their relevance in the area of astrochemistry. It is that on Earth, the specific selection rules are much more important than they are when we're talking about getting signals from space. Okay, that is it. And lastly, I solved a small problem concerning the derivation of this natural line width. Okay, right? So with this, I conclude this tutorial. And in the next lecture, that is lecture 63 and tutorial 17, I shall be giving you a sneak peek into the specific selection rules for electronic excitation and de-excitation involving atoms. Okay, right? Thank you so much.